Saxon Algebra 1, Lesson 94. Greetings, my students. Today we are going to talk about dirt problems. Once again, distance equals rate times time. Today we're going to cover type 2. Before I dive into what's new, let's review the type 1. And this, as you will recall, was the Lord of the Rings style problem, in which we have Frodo and Sam going to Mount Doom to throw the ring into the fiery gulf and then return back to the Shire. The distance to Mount Doom is the same as the return. I mean, the mileage may vary slightly in real life because, you know, they took the Eagles and it was probably a little different route, but pretend they walked the exact same footpath both ways. We remember that their distance to the mountain is the same as their distance back home. And taking advantage of the fact that distance equals rate times time, we can blow this out a little bit, if you will. And this is what we use for our base equation. Then we make a list of these and we look through the problem to find what we can about the various rates and times, and then we solve for what we don't know, right? But this is the basic picture. This is the distance equation, but this is the rate times time equation that we use to solve the problem. One slight variation on this problem can be found if we say, okay, this is Sam and Frodo, for example, going, and here's Gollum following them all along the way, the creepy dude. This also gives us a distance 1 equals a distance 2 scenario, and it fits the very same pattern of equation. All right, so this is what we've already covered. Now, type 2. Type 2 is not based on Lord of the Rings. Type 2 is based on the Titanic. Even if you have not seen the movie, I'm sure you are familiar with the story of the Titanic movie. I'm going with the fictionalized account. We've got Jack and Rose, right? Jack is the scruffy, lower class, working class guy who's riding in the lower passages, and Rose is the highfalutin lady. And they meet on the Titanic and they fall in love, but their fates are not destined to be together. They end up floating on a piece of wreckage in the cold North Atlantic after the ship has hit the iceberg, right? And sunk, it's freezing cold. They're holding on to a piece of wreckage, and yet Jack cannot climb onto the wreckage because then it'll sink and they'll both be in the water, and it's really cold, and eventually Jack drowns. Spoilers. Jack, their hands are together and then they slip away and poor Jack drowns and sinks to the bottom of the sea, and Rose floats on and is eventually saved by the Carpathian, another ocean liner that's in the area, and she goes on to live her life. Okay, so this is a story. These pictures fit that story. Here's the first example. Here is the ship, the Titanic, traveling from England. They're on their way to New York, but they're in the North Atlantic, and here is the iceberg into which they were bumped. The iceberg, I'm sure, was originally part of the Arctic ice sheet, and that has traveled, and they're on a path of destiny, and they bump into each other. This is distance 1 from England to where the accident happened. This is distance 2 from the Arctic ice sheet where the iceberg was born to the accident, and together they add up to a total distance called K. That's the distance from England to the Arctic place where the iceberg was born. It's where both of their trips began, and they meet in the middle, okay? So we write that as distance 1 plus distance 2 equals K, and K equals the total trip, if you will, the two pieces added together, okay? And we see, okay, it's the same thing where we've got distances and we can use distance equals rate times time, and we can change this. Rate 1 times time 1 plus rate 2 times time 2 equals the total trip. This is what we'll use as our base equation in these problems, okay? The variation on this is to say, here we have Rose and Jack floating on the piece of wreckage together in the water. And eventually their hands slip away from each other. It's so tragic. And Jack, sadly, sinks to the bottom of the ocean while Rose goes on to be rescued and makes it safely to New York. Okay? So the trips can go away from each other as opposed to here they went toward each other. Okay? So this is the ship and the iceberg going bump in the night. This is Jack and Rose together on the piece of wreckage. And I mean, technically Jack needs to go down, but we're drawing it in a straight line. He sinks to the bottom of the sea and she goes on to New York and lives happily. And that's, that's the sad distance between them. So here's Rose going to New York and here's Jack sinking to the bottom of the sea. The total distance that will be between them, and it fits the same pattern, D1 plus D2 equals K, and we use this the very same way. All right. Okay, there's one more thing that I'll need to explain to you about time, but I'm gonna do that in the context of the problem. All right, so now we're gonna do 1, 2, 3 problems that fit this type 2 scenario. In the homework, you're continuing to do the type 1s. Now we're doing the type 2s in this lesson, and those will start to show up in your homework. The hardest thing for a student new at this is figuring out which of these scenarios you're dealing with in a particular problem. Let the movies, if you haven't seen these movies, at least watch a trailer or something. I'm pretty sure this one is like PG-13. I don't know about this one. This is violent. This has sex in it. I don't know if your families are down with you watching these, but the more you can kind of wrap those stories around your head, the more you will be able to recognize the pattern when you see it in the problems, all right? And the third movie we're gonna use for the type 3 is Princess Bride. So hopefully you have seen that. That's in most families' bag of tricks. Okay, example 94.1. A southbound train has left Fort Walton Beach at 9 a.m. 2 hours later, a northbound bus has left the same station. So what we have is a scenario like this. They were together, then one went in one direction and the other went in the other direction. We don't have to worry about compass points or like drawing this accurately, north, south. We just know north and south, that's opposite directions, okay? So they're going away from each other. Now, as soon as I get that figured out, I stop looking at the problem and I go work until I get my base equation. I know that this is the first distance. I'm gonna call it the distance of the southbound, and I'm gonna call this one the distance of the northbound. It helps to put a letter there because it helps you match the words in the problem to the numbers and letters on your page. So I recommend giving these names whenever possible. We know that the total trip we call K. That's just random, I don't know why, but we do. Okay, so the distance of the southbound bus plus the distance of the northbound bus equals some total amount K, because they've traveled, right? And they stop at some point. We'll read the story in a minute and get all that straightened out. This, I remember that distance equals rate times time, so I'm gonna blow this out. The rate of the southbound times the time of the southbound plus the rate of the northbound times the time of the northbound equals K. This, once we get the R's and T's in there, we're good to go. And as you know from the lessons you've already done that allowed us to practice the mechanics of this, that's what it's supposed to look like, right? Now we need to make our list over here. RS, TS, RN, TN, K. All right. Now, once I got my list done, I'm ready to go back into the problem and try to find this information, and then I'll plug it in. All right. Now, here comes drama. This is the extra thing I was telling you about that we need to do. The southbound bus left Fort Walton Beach at 9 a.m. What? 9 a.m.? That's not how we're used to getting our times. We're not used to getting clock times, right? 9 a.m. is a clock time. Usually it tells us the bus drove for 2 hours or something like that, right? 2 hours later, a northbound bus left the same station, and then they stopped driving at 2 p.m. Those are clock times. When we have clock times, right, like 9 a.m., that's a time on the clock, that means we need to make a special chart to organize the clock times. John does not make this chart. It's a really great chart. You're gonna love it. It helps so much. All right, this is what we need to do. We need to have 3, it can be a fairly small chart. I'm making it actually a little bigger than I usually do now. And we're gonna have start, end, and hours, okay? After we make this once or twice, I'm gonna put S, E, and H, because who needs to write a million things, right? Then we're gonna put our 2 buses in here. This will be the southbound bus, and this will be the northbound bus. Again, if this wasn't the very first time you were doing this, I'd just put S and N. All right, now what we're gonna do is we're gonna use this chart to organize the information that we're given about the times. The southbound bus leaves at 9 a.m. Okay, so that's the start time of their trip. So I'm gonna write 9 a.m. here. 2 hours later, a northbound bus left the same station. All right. 2 hours later would be 11 a.m., right? If the bus travels at the same rate and we're 352 kilometers apart at 2 p.m., so their ending time is 2 p.m. Now we can figure out how many hours they actually traveled. Southbound bus started at 9. Okay, so this is how my brain does it. From 9 a.m. to noon, that's 3 hours. Then from noon to 2 p.m., that's 2 more. So that's a total of 5 hours. 11 a.m. to noon is just 1 hour, plus 2 more means 3 hours. Make sense? So I just used this information to calculate. Okay, now I've got my times. The time of the southbound bus is 5 hours. The time of the northbound bus is 3 hours. That's how we convert times on a clock into the hours that actually elapsed. That's what we need in the problem. Okay? Okay, let's go back. We said something about our rates. Oh, they have the same rate. So here's what we do. If the rates are the same, knock off the subscripts. Let's write that down. Just use R. If times are the same, knock off the subscripts and just use T. Okay? So that is going to help us in solving the problem because they aren't different variables now, they're the same. And the last piece of information we have is that if the buses traveled at the same rate, okay, we took care of that, and we're 352 kilometers apart, that means that's our total trip. At 2 p.m., find the rate of the buses. Okay, so here's what we did. We used the clock times given in the problem to calculate the number of hours. We put that in. We were told that they were the same rate, so we knocked off the subscripts and we'll just use R. There's the total trip. We plug that in. Now we're ready to take this and bucket it and then fill in. This is the part we've had lots of practice at. This is the part that's new and hard. Okay, so make sure your notes on this are complete. Rewind and let me say it all again if you're feeling confused by it. This is what's new and difficult in lesson 94. From now on, what I do is going to be fairly easy. Okay? We will do clock times again in the next 2 problems, so we'll get a chance to practice that some more. Okay, now I'm going to bucket. All right, and then I'm gonna fill in. That's why I like these in order, is that when I go to fill in, everything just fits in order. I don't have to think too hard. Okay, everything's filled in. There's nothing to distribute this time. This is an easy one. So I'm gonna write this now in a way that looks normal to me. 5r plus 3r equals 352. Then I can add like terms. And let's take 352 and divide it by 8. 8 into 3, nova. 8 into 35 goes 4 times, right? 8 times 4 is actually 32, so I subtract and I bring down, oh look, and I get 32 again. So that tells me that r equals 44. So that means that the rate of the buses was 44 miles or kilometers. Let's look and see. No, kilometers. So it's kph. I just look for the words in the problem. There's nothing magical about that. And then we double check what the question is. Find the rate of the buses. So it's 44 kilometers per hour. Okay? You can write it as kilometers per hour, or you can write it as kilometers per hour. Either way is fine. I don't have in this kind of problem, I don't have a preference. It doesn't matter to me. That's the right answer. Yay. Look how much space these problems take up. It's a lot. Feel smart. Second problem. I told you there are 3, right? A train starts from Toledo and heads for Mackinac, 332 kilometers away. Oh, stay right there. This is one of my favorite problems. I have a visual. Look, it's a little map of Michigan. I'm originally from Michigan, and it's such a great state because it's shaped like a mitten, as you may know, but it's super easy because you always have a map of it, right? In college, people would be like, oh, where are you from? And we'd all like point on our hands. I'm from a town that's about here, okay? Toledo is down here, and Mackinac is underneath the ribbon. Mackinac's up here at the high point, right? And then you know there's an upper peninsula to Michigan that looks kind of like a hand tipped this way. And so the train is going from Toledo to Mackinac. Oh, right? Probably right through my hometown of Brighton, Michigan. Okay. Thank you, Christmas ornament. Okay, so the train starts from Toledo and heads for Mackinac. At the same time, a train leaves Mackinac and heads for Toledo. Notice I'm ignoring all of the numbers in the problem. I don't care about those yet. I just want to understand what's going on. And what I get is that the trains are starting at the opposites and they're going to meet somewhere in the middle of that dang mitten, right? So this is the Titanic and the iceberg bumping, right? This is Toledo and this is Mackinac. Again, Toledo is down here. It's actually in Ohio. And Mackinac is right here. This is called the Mackinac Bridge that connects the lower to the upper. So this is Mackinac, Indian word. I think it means many waters. And they're going to meet in the middle. You don't really need to understand the geography to do this problem. I just like to tell you. This is Toledo. This is Mackinac. And in its purest form, it's spelled with a C at the end. Pronounced Mackinac, but it has the C at the end. That's Indian phonetics. John spells it like this. That's like the anglicized version of it. This is the correct one. This is what, us Michiganders, we're all about this. Okay, enough distraction. All right, so this is the distance of the Toledo train, and this is the distance of the Mackinac train. And we want to know, we're looking at their total trip. So we know it's this kind. dt plus dm equals k. It's a Titanic kind. It's the ship and the iceberg bumping. Let's blow it out. RTTT plus RMTM equals k. Notice we are multiplying the r's and the t's because we multiply rate times time to get distance, right? That's our overall. This is the goddess of these problems. It reigns over all that we do. All right, we have a base equation. Yay, let's write the list and then go mine the problem for details. RT, TT, RM, TM, K. And as soon as we see a clock time, we'll know that we need the chart. But at the beginning, we don't know for sure if we need it or not. A train starts from Toledo at 11 a.m. Dang it. Now we know we need the time, the clock times. They're not hard. It's just kind of a pain. It's just one more thing, right? To keep track of. So starting time, ending time, hours. That's what that stands for. I'll write it in because we're just beginning with this. But in the future, you can just use those letters. And then we have the train from Toledo and the train from Mackinac. So I'll just write the T and the M. All right, a train from Toledo starts at 11 a.m. It helps to put the AM and PM because when you're calculating the hours, sometimes that's good to know. And heads for Mackinac 332. So that's the total distance. It leaves Toledo for Mackinac 332 miles away. At the same time, a train leaves Mackinac. Okay, so also 11 a.m. And heads for Toledo at 65 kilometers per hour. So the rate of the Mackinac train is 65. If the trains meet at 1 p.m., and let's hope they meet gently and not in a fiery collision, what is the rate of the first train? Okay, well, when we look at this, we go, oh, look at all the blanks we have. But we can figure out our times right now. From 11 a.m. to 1 p.m., let's see, 1 hour till noon, and then one more. And they're the same. So both of the times are 2. Okay, that looks good. That's what we're trying to solve for, right? So now we'll take this and we'll bucket it. And again, you've done all the hard part. This is the hard part that we're learning how to do now. Solving is the easy part that you've practiced before. I go in order. The rate of the Toledo train times 2 plus okay, that's just me filling in. 2 times RT plus 65 times 2. Okay, I'm going to double the 60 and get 120. I'm going to double the 5 and get 10. 120 plus 10 is 130. Equals 332. I subtract the 130. That's the third best friend. This becomes 202 equals 2RT, right? That's what's left over. Divide both sides by 2. And we get that the rate of the train from Toledo equals 101. Whoa, it's flying. Kilometers per hour. Make sure you always put some sort of a unit on your answer. The rate will be the complicated one. Distance is miles and time is, it's usually hours. It could be minutes or seconds or whatever, but it's usually in hours. All right, yay, that's the right answer. We're getting it, right? Okay, let's do one more. Example 94.3. The ships were 400 miles apart at midnight and were headed directly toward each other. Okay, I ignore the numbers and I just think about the picture. They're away and they're headed toward each other. It's kind of like the ship and the iceberg. It's so Titanic, right? And I don't worry about drawing these proportional. I don't know which one of these guys took the longer trip. I just make them meet in the middle. It doesn't really matter. Okay, so this is going to be the distance of the first ship and the distance of the second ship. I'm just going to use 1 and 2 for this one. John uses F and S for first and second. Whatever, that works too. Okay, so the distance of the first ship plus the distance of the second ship equals the total trip. And so I know I can do, wait, I went too far. R1T1 plus, this is my favorite, R2T2 equals K. There is a lovely base equation that we can fill in, and we make our list. Now we'll go mine the problem for some numbers. We'll see if, I don't assume that it's clock time. I just wait until I get into the words. And then if I need the little clock time chart, I create that when need be. The ships were 400 miles apart at midnight. Okay, so 400 miles is the total distance. And midnight, dang it, that's a clock time. So we know we need it. All right, this is ship 1 and ship 2. This is the start, this is the ending time, and this is the number of hours that elapsed. Okay, they start at midnight. And we're headed directly toward each other. If they collided at 8 a.m., okay, blah, 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 it goes and gives me other information. But this tells me, okay, this is pretty easy to figure out. From 12 to 8 a.m., that's 8 hours for each of them, right? So we can fill that in on our chart. If they collided at 8 a.m., find the speed of both ships if one was 20 miles per hour faster than the other. Now, because we don't have a lot of distinguishing information on these ships, we don't know which one's faster and which one's slower. It doesn't really matter. And I guess that's what John's F and S stands for now that I think of it, faster and slower. But it doesn't really matter. What we can just do is say, okay, let's say that R2 is the slower ship, so we'll make that plus 20, right? Because this would be less, and then when we add 20, that gets it to equal. So, but it doesn't really matter which, if R1 is the faster or the slower, just as long as we write an equation that makes sense. That would make this one the faster, this one the slower. We add 20 to the slower one, now they're equal. Okay, now we can plug in. That was really hard, by the way. I went over that fast, like, oh yeah, obvious, right? That's hard. Okay, R1 equals R2 plus 20. Whoa, squeezing. T1 is 8. R2 we don't know. T2 is 8. And K is 400. Now I'm going to have to distribute, which isn't hard, but that bracket was so little, that bucket was so tiny that I squished it. So I just have to be careful. 8R2 plus 160 plus, write that in the right order, 8R2 equals 400. Now I will combine these like terms. At the same time, I swim the 160. Remember, what's important here is that these two are on the same side of the equal sign, so we can combine them without having to swim them. This guy has to go across the equal sign, so that's why we have to swim him with a minus, right, by doing the opposite. That can be really tricky and confusing, a subtle little difference. All right, so we're going to get, that goes away, we get 16R2 equals 240. How do you feel about that? Looks pretty good, right? Divide both sides by 16. 240 into 16 into 240. 16 goes into 24 once. Bring down the 0. 8 times 10 is 80. So 16 is twice the 8, so that tells me it goes 5 times. I don't know if you followed that, but 8 times 10 equals 80. I've got 16, which is twice as big as 8, So I know if I multiply it by a number half as big as 10, that will also work out. See the pattern in the numbers? So this R2 equals 15. That's the rate of the slower, right? Because we added the 20 to it. So we add 20 to get R1, and that would be 35. Neither of these ships are going very fast, are they? And they are mph. I just looked to see if the distances are measured in miles or kilometers. This is the right answer. Yay! All right, this is challenging, you guys. Keeping these straight is a challenge, and wait till we get to that third kind, which is based on The Princess Bride. I do highly recommend that you watch these movies and get these patterns of travel really firm in your mind so that it will help you identify what's going on in these problems. It really does help. I know it sounds a little crazy, but it does. Okay, that's lesson 94. Thank you. Goodbye.